I'm delighted to see two Borweins here, father and son. I feel honored to be able to speak here. This is joint work with one of them. I'm not sure if this is a true likeness. Please consider this the abstract of my talk. Anyway, there are various types of generalizations of the Riemann zeta function, and one that has been studied quite extensively recently is this one. With classical analytic methods, it's easy to see that it converges when these properties hold. And this sequence was first, this double series actually was first investigated by Tornheim in 1950, independently by Mordell for the special case when the three exponents are the same. And therefore, often they're called Tornheim sum, Tornheim double sum, or Mordell Tornheim sum, or double sum, or series. There doesn't seem to be a fixed terminology. And Witten in 1991 studied a wider class, and therefore Don Zeta in 93 in an article called them the Witten zeta functions. And therefore, now recently they've been called Mordell, Tornheim, Witten sums, or Witten zeta functions. Now, they can be analytically continued, just like the classical zeta functions. And it has been shown that there are poles when these one of these conditions are satisfied. One has to be a little bit careful about what it means, analyticity and so on. This is analyticity in each variable separately. So you can consider R and S to be fixed, and then we have a pole in T, and vice versa. So we have to be a little bit careful. I come back to that later. So this analytic continuation was also independently found by three Japanese mathematicians in 1990. Now, very recently, in a preprint of last year, Romick studied the analytic properties of this and studied it in greater detail. And he introduced this function where all three exponents are the same. It was already known to Mordell that omega 3 of 2n is a rational multiple of the 6th n power of pi. And these can be given explicitly. For instance, omega 3 of 4 has this form. Here is a picture of omega 3. It's an egg-shaped planet, obviously. Here is another picture. Anyway, back to the properties. Omega 3 of minus n is 0. That was shown by Romick. I'm not sure if he was the first one to show that. The recent literature is quite extensive, and I must admit I haven't read every single detail, but I believe that Romick was the first. Also, Zeta proved this identity. Zeta 2k, of course, is a rational multiple of pi to the power 2k, known since Euler, and this is, of course, well, we don't know much about the properties of this. And independently, Hewitt, Kenneth Williams, and Nanyue proved this result as well. And I should also mention that Mordell's original result for 2n, instead of 2n plus 1, had the same shape, where in addition to zeta 2k, we have an even zeta function. And that explained the rational multiple of the power of 6k. So here is an example. You just plug n equal 2 in here and we get this. So zeta 11, 13, and 15 occur. And the powers of pi come through Euler's formula to this, and then Bernoulli numbers are involved as well. Omega 3 of S has simple poles. That follows, no, actually that was shown by Romick, and he also determined the residues, and there are no other singularities. Now the main purpose of this talk, finally getting to this, is we want to study the behavior at the origin of this, so where S is 0. And also, we want to find out what is the derivative of this function at the origin, and look at a few generalizations. Now, so far, I haven't said much about the experimental nature of this. I'm coming back to this later. It is important to note that care must be taken in how we approach this, because, as I mentioned before, we have analyticity separately in R, S, and T. So this is essential. Now, first, Romick in his preprint showed that omega 3 of 0 is 1/3. And here, we will give it a different proof. And second, in the same paper, Romick showed that omega 3 prime at 0 is this expression, and he was able to actually evaluate it through these digits. Now, this is where experimental math enters in a crucial way. John used higher precision evaluation and the famous PSLQ to conjecture the following stunningly simple expression, log 2 pi. So compare this with this, and I must say, without knowing that this is what we expect, and this is what has to be true, it would have been very difficult to even approach proof. So this really gave us guidance. And so this is the main part of this talk, to give you an idea of what is proof. So, and I'm going to talk a little bit about a generalization. First of all, we have to talk about some special functions. The Pauli logarithm is, I think, it's fair to say it's one of your favorite special functions, John. It occurs in all different, or in a large variety of different settings in number theory and in analysis. It is defined by this series. Originally, where z in absolute value is less than 1. Here are some special cases. Order 0, we simply get the, obviously we get the geometric series. Order 1, that's where the logarithm comes in. So order 1 is basically the logarithm, and the Pauli comes in through higher orders. When z is 1, well, here we require this to be less than 1. However, if the real part of S is bigger than 1, then this condition can be relaxed, and for 1, we get the zeta function. So the zeta function, the Riemann zeta function, is a special, can be seen as a special case of the Pauli logarithm as well. And here is a crucial lemma. The Pauli logarithm can be written as an infinite series with the Riemann zeta function occurring, powers of the logarithm, and some kind of an error term. This is a known a well-known representation. For instance, it can be found in the famous 3 volumes Higher Transcendental Function by Erdely and others. There is also let's go back. You will see that S is not allowed to be a positive integer. The reason is, if S is a positive integer, we get zeta of 1 here. And also gamma of negative integers, and we have poles there. So, however, there is a more complicated variant that also holds for these. It takes care of those singularities that would otherwise occur. Now, here's the connection with the Witten Zeta function. So let's get back to that. Gamma of t. This t is a little bit different. Gamma of t times this can be written as an integral involving 2 polylogarithms of order r and s, and the t occurs here. Now the proof is fairly straightforward. We start with Euler's integral for the gamma function, which is often seen as the definition of the gamma function. Make an easy substitution, and we get this. And now we replace t by we replace s by t, n by n plus m, and just rearrange it, and we get this. So here you already see we get this n plus m to the power t, and here we get it. And now we plug this into the definition of the Witten Zeta function, where you will remember we also have 1 over n to the power r, 1 over n to the power s, or the other way around. And we plug that in. Interchange the double series with integration, which is allowed. Then these things occur, and they are simply the polylogarithms. And we're now, the main tool for our results is a remarkable identity due to the late Richard Crandall. I think John mentioned Richard already in his talk. And it uses a free parameter, and it is convenient for both theoretical results, as we will see here, and also computations. And of course, the computations led to our theoretical results. But first we need another special function, and it's the incomplete gamma function, the upper incomplete gamma function. Euler's integral for gamma of A is the integral from 0 to infinity. And now there are 2 types of incomplete gamma functions. The lower one, which will go from 0 to z. It's usually spelled with a small gamma, and the upper one, usually spelled with a capital gamma, goes from z to infinity. And obviously, when z is 0, we get the gamma function back by Euler's integral. Now, this looks like a mouthful or a screenful, but if you look at it a little more closely, you see it's not that bad at all. There is a lot of regularity in this formula. This is a double sum. These are 2 simple sums and a simple term, and it will become apparent.
You can take over.
So here is welcome to the speaker of this talk, Mark Chamberlain. Okay, so as you will see in a moment, it comes about in a very straightforward way, although it looks complicated at first, but it is remarkably useful. And now once again, let me scroll back, you will see that R and S cannot be positive integers for the same reason as before. So they must be excluded because Otherwise, zeta 1 or gamma at negative integers would occur, and we know there are singularities. However, these singularities cancel if we are careful. And the careful analysis gives another identity. It wouldn't be a screen full, it would be two screens full. So I will not give it here. And that is valid for all R, S, and T. And this and the previous screen gives another analytic continuation to all of C cubed. Once again, we have to be a little bit careful, separate in each of the variables R, S, and T, with the exception of the known singularities, the singularities that I showed a little bit earlier on. Now, let me sketch the proof. Just as we did before, we use the defining integral, the Euler type integral, make another simple substitution, and we get this identity. And once again, you see m plus n to the power t in the denominator, only this time we have the incomplete gamma function in the numerator. Now, we use the same argument as in the second of the two lemmas that I showed a while ago. And here is the key trick, and it's a very simple trick. We split up the integral into two parts, from 0 to some theta, and from theta to infinity, where theta is a positive real parameter. And then, so the order is flipped here. Theta to infinity, that's here, that gives rise to this. And the first one, that gives rise to that, just like in that lemma that I showed a little while ago. And now we use this expression for the polylogarithm, the one that where Zeta can be found in the book by Erdely. And here it is again. If we plug that in here, you see that we get from these parts, we get a double sum, and then we get the cross products, which gives us two separate single sums, and the product of these together, which give us that last symbol, the last single term. And we expand, integrate, and we get that screen full from before. And that is our essential, not our, it is Crandall's essential formula. So as a first application, we set R equals S equals T, and then we get our omega 3 with the gamma of S in front. It simplifies a bit, but the same structure again. We get this incomplete gamma term. We get our double sum. I sometimes talk about a troublesome double sum, but it's not that bad. And instead of two separate single sums, we get, well, two of the same single sums and that individual term.
Is that supposed to be an S in the bottom line?
It is supposed to be. Sorry?
The power and gamma, shouldn't that be 2 or something?
It is supposed to be a 2. Thank you very much. I just wanted to see if someone paid attention.
I think you're pro.
That line works only once. Okay, so what we do now is we multiply both sides by S and let S go to 0. If we do that, then S times gamma S approaches 1. That comes from the Laurent expansion, the well-known Laurent expansion of the gamma function about 0. So we get 1. So this disappears. On the right-hand side, we get S. And unless we have an S in the denominator, all the terms will be 0. And in fact, almost everything disappears. Especially this disappears, which is important. So the only terms that do not disappear, well, they will come in these two lines. So in the second row, if U equals V equals 0, Then we have an isolated S here, which get cancelled, and we get zeta of 0 squared, which is 1/4. In the third row, there you see when Q equals 1, then this disappears, and we get a 2S downstairs. It cancels against the S, and we get 1/12. Add the 2 up, and we get 1/3. So a very easy, it comes out almost immediately from Crandall's form. A few remarks. This also, we can basically read off the singularities and their residues. So they are immediately apparent just by looking at that formula, but we're not going to do that. And then with only a small variation, we can prove a more general result. Instead of making all three equal, we just put a tau, a parameter in front of that. So make the third one either larger or smaller and let it go to 0 in a different way. And then this becomes this formula. And of course, when tau is equal to 1, we get this tail will be 4, and we get 1/3 back. And here we see that it is very crucial to know and realize how we approach 0. Okay, so here we approach 0 in a different way. We get a different value at 0. Okay, that is important to realize. Yeah, and as I said, in particular, we get all 1/3. And now the derivative. That's the last and most important part. So what we do, we multiply both sides by s. We take the derivative of both sides. On the left-hand side, oh yes, what we do also, we have to isolate the singularities that occur here. So we put them on the left-hand side. If we do that, these are the singularities. I also isolated some terms that will give us a little bit of trouble, some singularities, and most of it is harmless. Now we take the derivatives of both sides. The left-hand side, well, that's just first-year calculus for a bright student, and we get this. On the right-hand side, actually, well, also first-year calculus, the product rule, but s goes to 0, so the derivative is simply the big bracket evaluated at 0, nothing else. Only a little bit more challenging, because earlier on, when we let the right-hand side go to 0, there was an s in front of it, which made almost everything disappear. Now it's a little bit more challenging. So, as I said, it amounts to evaluating this. Theta is a free variable, so once again, we consider theta going to 0. And that, now the theta going to 0 makes almost everything go away. But there are singularities at theta. Now, in the variable theta, there are singularities at theta. However, they cancel, and that's the key thing here. Now, some key ingredients, of course, I cannot give the whole proof, but just to give you an idea. This sum turns out to be this integral. Now, this gave us the most trouble. What to do with this integral? The first thing you do, of course, you go into tables. Tables by Grudstein and Rizhik, and this 3 to 5 volume Russian tables by Prudnikov and others. Couldn't find it. So if you can't find something, you find something similar. Okay? This is also experimental mathematics, not with a computer, but with a table. So sometimes old-fashioned tables are remarkably useful. And so this was the one we found that was most similar to that. Still different, but it gave us a handle, a very important handle on this was basically finding this provided the breakthrough. Because we have a gamma here, we have a zeta here, everything that we needed. And that was found in Grudstein and Bridges. So everything put together, we get, after some work, that's a slight understatement, we get this with an error term there, which of course goes away as theta goes to 0. And nasty singularity here at 0. However, this singularity cancels. So everything put together, we do get our theorem. So what was at first a beautiful observation finally turned into a theorem without, as I said, without the numerical observation. Most likely we would not have been able to find it, or we would not even have looked for it. Now, as before, we can do it with the parameter tau, and now very quickly a few extensions. We can look at a multidimensional analog that was studied by Matsumoto and by David and Jon very recently. And in analogy, we can define something like that. And very recently, a bright undergraduate student of mine showed in her honors thesis that we get this for n less than or equal to 7, and it's almost certainly true for all n. We just haven't closed the last gap in the proof yet. So, and then of course, when n is 2, we get 1/3 as before in the traditional. So this is work in progress. Also, the derivative, and Haley did that only for 4, and we get this. In addition to the log 2 pi, we also get zeta of 3. And I kind of know how to extend that to everything, but to arbitrary n. But this too is work in progress. And character analog, again, in another even more recent paper by David and Jon, we can look at alternating zeta functions and look at analogs. Some things become easier, other things become more complicated. So that is also work in progress. I'm pretty well out of time. So Jon found these results already. So the analog is 1/4 evaluated at 0, and the derivative is this term, again with a log 2 pi here, but a little bit more complicated. And yes, character analogs can also be studied in general. And so I want to close with the remarks, since this conference is all about experimental mathematics. Many of the results of this talk, not just the key results that I mentioned, were first obtained experimentally before they were proved. And knowing what to expect provides a great deal of guidance as well. Once we have a proof, it provides certainty that because we all make mistakes when proving, and probably we make more mistakes than a computer would make. And I'll skip over the last few things that I want to say, and